But let's take a look at natural gas here. So one of the things is we know the composition, then we want to know a little bit about its structure. So what they're trying to show here is the structure of methane. Methane is a common name for this, CH4. There are other names for this, but what most people do is they just memorize. CH4 is methane. And if we look at this structurally, what they're trying to do is they're trying to show the three-dimensional shape of this. And so we can see the hydrogens are bonded to the carbon with these lines here, but some of these lines form a wedge and some of them form a dash. So a wedge line represents something coming out towards you, and a dash line represents one going in. So this is four lines or four bonds holding the hydrogens there together. And three-dimensionally, we call this a wedge dash diagram, which can be represented with these ball and stick models. This is a computer-generated ball and stick model, but there aren't actual sticks holding the hydrogens to the carbon. What is a bond? The bond is just these atoms coming together, attaching. And so the advantage of using ball and stick is it's easier to see the shape of this from different perspectives. One of the perspectives that we see is the angle here. This is a more realistic picture of what the molecule looks like or would feel like to a probe. But with the ball and stick, we can see the angles here. And this angle is special. This angle is 109.5 degree angle. It's called the tetrahedral angle. And so all the angles are the same, 109.5. And this has a special symmetry. This is called spherical symmetry. So if you put this in a ball inside a sphere, it would be perfectly balanced. So it's kind of like a ball. And it should roll like a ball as well. And so this is a tetrahedral. This is a composite where they put the space filling and then they have the ball and stick in there so you can see how the atoms are arranged. It would be easier. But the space filling would be the most accurate representation of this molecule. But sometimes it's hard to see, so the composite or ball and stick was used instead. So there are different ways. Sometimes we don't have to go full three-dimensional for this. But we can. We can try to draw a ball and stick here. So we draw two. This is about a 109 degree angle, and then we draw a wedge. That's 3, and then a dash. This is 4. So we have 4 hydrogens bonded. One of the chemical properties of methane is it's combustible, it's flammable. It's a gas. And so this is CH4 gas. So if you visualize it, the gases are moving with high translational, vibrational, rotational energy. So these are moving about. But they're separated. They're not stuck to one another like liquids would be. They're combustible, but we need what we call an oxidizer to burn methane. And so what's the oxidizer that we use? The oxidizer that we use is the prototypical oxidizer, which is oxygen. And in fact, that's where the name oxidizer comes from. Because oxygen is a common oxidizer. It's present in air at about 21%. And so oxygens have a different structure like this. Oxygens like to pair up. And what they form is they form molecules that look like this. Now, molecules are 2 or more atoms bonded together. This one's called a compound over here. A compound has 2 different elements or more bonded together. So here we have the element carbon, we have the element hydrogen. We have 4 hydrogens to every carbon. So it's a compound. This would be an element, but it's a molecular element. It forms what we call diatomic, di meaning 2 atom molecules, diatomic molecules. 2 atom molecules. Don't worry about these dots. These dots represent electrons. We'll talk about those later. But if I take one methane and then combine it with 2 of these oxygens, like this, then we have a explosive mixture. This is just the right mixture. It's just the right amount of oxygen. And what just the right amount of oxygen is, we represent it like this: 2O2. These are also gases. So these would have vibrational, rotational, translational motion associated with them. But this would be an example of a chemical change. In a physical change, nothing really changes. So, if we take methane, we could liquefy it and get liquid methane. Have you ever heard of liquid methane? I see buses driving around with LNG. Have you ever seen LNG? LNG means liquefied natural gas. So liquefied natural gas is essentially liquid methane. And the reason why is gas has a lot of empty space. So if you fill up your gas tank with lots of empty space, that's not very efficient. And so they want to get rid of the empty space. One way of getting rid of the empty space is to compress it down so that it liquefies, so that it forces the molecules to come together, form a liquid. And so liquid natural gas packs a lot more fuel per gallon than natural gas would. Because a gallon of natural gas contains mostly empty space, but a gallon of liquid natural gas would contain lots of methane. In Santa Barbara, liquid natural gas was very controversial. There's a lot of natural gas in Santa Barbara, and you know what they do with most of the natural gas? They just let it escape into the atmosphere. Well, natural gas is actually a much worse greenhouse gas than CO2, so they should try to make an effort to capture it. And so one of the ideas that somebody had was they're going to capture it and then liquefy it. Because if they put it on a ship as natural gas, it's kind of wasting a lot of space because gases have lots of empty space. But instead, if they could liquefy it, then it would be much more economically efficient to transport it. And so I remember this very well because I was in high school at the time. But there were huge protests. The citizens of Santa Barbara did not want any LNG. And so, you know what they're afraid of? They're afraid of one of these big ships out in the channel exploding and killing a bunch of people. So eventually, they dropped the plans for liquefying natural gas. Natural gas is just exploding into the air. But,
So when methane gets really toxic, it causes an explosion?
It potentially can cause an explosion. So that's what people are afraid of. People are afraid that they're going to die, the LNG explosion. But, you know, the other day I was following an LNG bus and I was thinking about the same thing. Is it going to explode? Am I going to die? You know? Because when you mix gas and air, you have a potentially, what? Explosive mixture. And if it does explode, there was you know, this was what people were afraid of because natural gas explosions happen. And then NYC was one that was recently, it was a 5-story building. Let's see if I can see it. Do you see this one?
Yeah.
It's a natural gas. This used to be a 5-story apartment building in New York City. This is in 2015. Huge explosion. It's a death toll. It's only 8 people died. You would think a lot more people would have died, but I think it was in the middle of the day. Most people were at work, unfortunately. But, you know, I wasn't worried about it exploding. Even though I was following the CNG bus, you know, you just have to take appropriate precautionary measures. It was the same thing here. Maybe there's a natural gas leak. Unfortunately, nobody detected it, the smell. You know, if you detect smell of natural gas, the gas company will come out and look for it for free. You know, just call them, come to your house, try to find where it's leading from to prevent something like this from happening. And so, but it's got a lot of what we call kinetic energy, or a lot of what we call potential energy. It's got the potential to explode. This is at room temperature. We like to keep this at room temperature. It doesn't have to explode. It could just generate a fire. We use the fire, and actually, a lot of people want to ban natural gas stoves. Do you know why? Like, for example, they want to ban all gas appliances, stoves, ovens, whatever, gas. And so LA and I think San Francisco have banned new restaurants from having gas stoves. But you know, that's tricky because have you ever if you're a cook and you're used to using gas, it's hard to switch to electric. It's just harder to.
There's an outage.
Yeah, and so to make all the new restaurants go electric is going to be tricky, I think. It's not doable for some people. Some people will absolutely refuse to use electric and they're going to stick with the gas appliances. But the reason why they banned them for new construction, and eventually they want to do residential too, they're looking at banning all gas appliances, whether commercial or residential. But this is the reason, because it's forming this. This is an example of a chemical change. And what do we call this? Well, this is the structure. I'm trying to draw the structure. But this is 1 carbon and 2 oxygens. And we would call this carbon dioxide. Yeah. Carbon with 2 oxygen, dioxide. And so carbon dioxide, unfortunately, is one of the culprits for global warming. Methane is also. And so this is why they want to get rid of cows. They want to get rid of cows because, cows produce a lot of methane. Did you know that? And they're worried about methane emission. And methane is the worst greenhouse gas than CO2. So not just stoves, but cows. Well, rather than getting rid of all the cows, there are some chemists that are trying to figure out how to change the stomach chemistry in cows so that they generate less methane. And so they're trying to feed them certain types of food and certain types of chemicals so we don't have to get rid of them. Because I think there is a push to get this order. What's that?
Wouldn't that create more problems though for us with those genetically modified stuff that they're feeding them?
They're feeding them? They're not modifying them genetically. What they're doing is they're adding additives so that these chemicals will react with the methane, or they will react with some other things to do that. This is the same concept behind diesels. Diesels are heavy polluters, but and Volkswagen, Mercedes, a whole bunch of manufacturers had diesels, and what they did was they put additives in it. And so there are things called blue tech. Have you ever heard of that? Mm-hmm. Blue tech, where they injected certain chemicals into the exhaust to react with the nitrogen. Diesels produce a lot of what we call NOx, oxides of nitrogen. These oxides of nitrogen create a lot of pollution. So they are injecting chemicals into the exhaust to react with it. This is the same kind of thing. They're having the cows ingest chemicals, and they're getting chemical reactions to take place to generate less methane. In fact, there's an article about this if you're interested in it. Let me find that article here. There's a news magazine, a weekly news magazine called C&D News. And this is chemical and engineering news. And so you can find a lot of interesting stuff. Like if you look, there's all like hydrogen power. Hydrogen power right now is huge. They're looking at green hydrogen, purple hydrogen, red hydrogen. Have you heard of all these hydrogens? Depending on how they make it. In fact, Toyota is trying to make and I test drove one of these. Um, Mirai. Have you ever heard of the Mirai? Toyota Mirai. It's a hydrogen-powered vehicle, and on 190th Street, between Crenshaw and Western, there's a hydrogen filling station, and on Prairie, there's another hydrogen filling station. So you can go to those and then get hydrogen for your vehicle. And what they use the hydrogen for is they use it to generate electricity. So I test drove a Mirai. They had at the mall in Manhattan Beach, they had a bunch of Mirais there. And if you test drove one, they gave you a $25 Simple Green gift card. It was pretty nice. So but it was interesting. It drove just like an electric car. And so they're looking at hydrogen, but the price of hydrogen, with gasoline skyrocketing, the price of hydrogen skyrocketed as well. So somebody was telling me that they spent $200 to fill up their hydrogen car, whereas the gas car would cost maybe $60 to fill up, for the same mile, something like that. But they're trying to bring the cost of hydrogen down. And so one of the more promising ways of bringing the cost of hydrogen down is by using or generating hydrogen in certain nuclear power plants. There's certain kind of nuclear reactions that are trying to generate the hydrogen. But the infrastructure is not there. Infrastructure for electric cars is much greater, the plug-in electric cars, but still, even that is tough. I have an electric car too. But the electric car, sometimes you go to charge it, unless you charge it at home, but if you go to the charging station, sometimes there's a long wait at the charging station. People are getting upset at the hydrogen charging station, and people are, no, I'm next, or whatever. And then they're protecting their territory. What's that? Oh, yeah. Yeah, you got to worry. You're right. The carbon, it depends on how they generate electricity. So a lot of electricity is generated. You know how most electricity is generated? Burning coal, I think, is number one, and the burning coal is mostly on the East Coast. But on the West Coast, you know how most electricity is being generated is by burning methane and natural gas. And you burn natural gas to make electricity. But there are other ways of making electricity. So this is why Toyota is promoting their hydrogen, because that leaves a zero carbon footprint. They have zero carbon footprint, and this is the way to do it. But there's another engine that's being developed by Toyota too. And rather than using carbon-based, like methane's a great fuel. We'll talk about why methane's such a great fuel. But there are other things that look like methane. One of them that looks like methane is right next to it, is nitrogen. And when nitrogen and hydrogen come together, we can make ammonia. And so rather than burning methane, they want to burn ammonia. And so it's ammonia vehicle. But anyway, let's take a look. And so chemists are all involved in, and most chemists are, are interested in this type of stuff, green chemistry. But let's take a look at the feed. This is research, I think, at UC Davis. So there's some food chemists, I think, look at UC Davis looking at what to feed cows to reduce their emission. And UC Davis is the big agriculture school in California. So this is an article I read not so long ago. This is 2015. I don't know what's been done since then, but they give them a small molecule for these animals in the food, and then apparently it reduces methane emission by 30%. It's pretty big. I don't know how that affects dairy milk or if it's cattle or cows. Steak or whatever, meat. But this small molecule, it says without disrupting a cow's digestion. And so, what is it? And so, mixed additives containing 3 different concentrations of 3-NOP as well as a placebo additive when they administer. So, it's pretty interesting how they're trying to look at this. And so, this is, I thought, pretty creative. Rather than banning the cows, they're trying to figure out ways to reduce emissions. The same thing with methane burns very cleanly. I mean, we burnt the methane in the Bunsen burners in the lab, but did we worry about poisoning? Not really. You know, we did worry about carbon monoxide, so we worried about the yellow flame, but we didn't necessarily worry about poisoning because it burned so clean. But it's possible to scrub it. And so what people are trying to do is they don't want to ban the power plants. What they want to do is they want to continue the methane power plants, but they want to see if they can capture the methane that's being produced or the CO2, let's say, the CO2 that's being generated, or this kind of stuff, or that kind of stuff. So people are looking at creative ways rather than an outright ban. And so maybe rather than banning gas appliances, maybe they could figure out other ways to do it. And then maintain certain things. So that's what's happening now. But anyway, CO2 is another greenhouse gas, and people are worried about that. But what else is formed? So the atoms get rearranged in the chemical change, and so we have these hydrogens and we have these oxygens, and what else is formed is this. This would be what? Water. Or another name for water, which nobody ever calls it, would be DHMO. What does DHMO stand for? That's correct. Dihydrogen monoxide. And so dihydrogen, 2 hydrogens, 1 oxygen. Dihydrogen monoxide, nobody ever calls it that, and so it's unfamiliar, so that people might be confused. Did I talk about the DHMO, dihydrogen monoxide ban? Yeah. Well, we don't want to ban it, for sure. But anyway, what we need 2 of these waters to form. And it depends on the temperature. So what we do here is we start off at 25 degrees C, but you know what the flame temperature is? Is the flame at room temperature, or is the flame much hotter than room temperature? It's much hotter. In fact, the flame temperature is more like 800 degrees C. But eventually, does it stay hot forever? Does the CO2 that's generated in water stay permanently at 800 degrees C, or what happens? No, the heat dissipates. And the heat dissipates, eventually cools back down to 25 degrees C. So what we do is we start off with methane and oxygen at 25 degrees C, and we end up with CO2 and water at 25 degrees C. But like matter, like atoms, you see the atoms are just rearranged here. We don't have any atoms disappearing, and we don't have any atoms magically appearing. And so all the atoms are accounted for, they just get rearranged. Well, it turns out the same thing. We have conservation of matter, or conservation of atoms, and we have conservation of energy. That is, we have all this potential energy. This was a potentially explosive mixture. What happened to all that? Am I going to worry about CO2 and water blowing up a 5-story apartment building? No. I mean, if somebody kept some sparkling water in their fridge, you wouldn't expect that much damage. And so there's a lot of lost energy here. And that lost energy is not kinetic energy, because we start at 25, we end at 25. We wait for this to cool back down. It's not going to stay hot forever. But where did all that energy go? All that energy was released into warming up the surroundings or destroying a building. And so here, energy is conserved as well. And so in this equation, this is called the chemical equation, I have mass or matter being conserved. So the total weight initial is equal to the total weight final. And I have energy being conserved. The total energy initial is equal to the total energy final. Now, how much energy is this? Well, we want to be quantitative, but right now, we're just going to be qualitative. It's just some amount of energy to balance things out. So when we look at the total energy, what does the total energy equal? It doesn't equal. Some people put this down. Some people put the total energy is the change in kinetic energy. Is the total energy the change in kinetic energy? No, when I look at this, what is the change in kinetic energy here? So if I start off at 25 degrees C and I end up at 25 degrees C, was there any change in kinetic energy? No. In fact, in this case, the change in kinetic energy is zero. If the change in kinetic energy is zero, does that mean the kinetic energy is zero? In other words, what happens when the kinetic energy goes to zero? Do you know what happens to the temperature when the kinetic energy goes to zero? What happens when the kinetic energy goes to zero is kinetic energy is a measure of what? We keep them separate. Don't mix up kinetic energy and potential energy. We try to keep those separate all the time. But we can have a change in both. So for example, if I waited, let's say I went from 25 to 800 degrees C. And so I have CO2 at 800 degrees C, 800 degrees C, let's say CO2 and H2O. This is just going to be really exciting. But they aren't going to stay excited forever. And so that means this is high kinetic energy and high or low potential energy, let's say. And eventually they'll cool down. Cools down, we release it. And so we try to keep it separate. So if we start at 25, we like to end at 25 so we can see what's happening with the potential energy, if anything. Sometimes we increase the temperature, decrease the temperature. So, if we start at 25 and went to 50, then we'd have to wait until this goes from 50 degrees C back down to 25 degrees C. Once we go back down to 25 degrees C, then it's reached room temperature again and stops. So kinetic energy is a measure of what? Motion. Yeah. It's a measure of motion. So if there's zero kinetic energy, there's zero motion. If there's zero motion, what's the temperature? Absolute zero. And so, is this at absolute zero? No, that means there's kinetic energy there. This is not at absolute zero. There's kinetic energy there. So we have kinetic energy here, we have kinetic energy here, but the delta KE can be zero. Right? Because we start at 25, we end at 25. So this is wrong. So some people put that the total energy is the change in kinetic energy. No. It's not delta. And the same thing, they put delta PE for potential energy. That's incorrect also. I want what we call the absolute energy. And so when we look at the total energy, what is the energy of this?
Does it depend on the bonds?
Yeah, that depends on the potential energy. The bonds are holding this together. And we're rearranging things by breaking bonds and forming new bonds, essentially. That's what we're doing when we're rearranging these in a chemical change. In a physical change, there's no rearrangement. So what happens is this starts off as a gas. It's steam. You don't have liquid water in the flame. And eventually that steam will condense into a liquid. That is, in steam, there's a lot of empty space. The particles are moving very fast. And then when we liquefy, the particles come together and they get stuck. They're sticky. And they stick together and form the liquid. And so that would be an example of a physical change. And so here we have the chemical change. That's what we want to do. Right now it's just qualitative. Later on we'll look at trying to figure out what the energies are. But right now we just want to get a conceptual part of it. Later on we'll look at becoming more quantitative. It's not so easy, it turns out. Getting the kinetic energy is very easy because we have Newton's laws to figure out, because Newton did the laws of motion. We could use Newton's laws for them. Potential energy turns out to be a much more difficult task. And we'll talk about that when we get to the theory of chemistry. Does anybody remember the theory of chemistry? What it's called? Just the name of the theory.
Quantum mechanics.
Quantum mechanics, good, good. It was much faster than this morning. It took maybe about 4 or 5 minutes until it clicked. But
So the question is like, how is energy released after they react?
energy is released to do different things. So what most people do is they use this to boil water. You put a pot of water on the stove, and you want the energy to go into the water and heat up the water to get it to boil. But in the building, the energy was released to break apart the building structure. So, that building was completely demolished by all the energy that was released in that explosion and the subsequent fire that happened. And so the energy can be done, dissipated in different ways. So this was interesting. Like like in Japan, those airplane that landed on top of another plane, and then the passengers on the plane I guess got on fire, and passengers on the plane exited by the slide, and it was some ridiculously high number. I thought, wow, they said that it was like they could evacuate 100 people in like 1 minute or something on the slide, and I thought, wow, that is incredibly fast. But I thought, wow, that's impressive. And so in that case, they're starting off at high gravitational potential energy, and then when they hit the bottom, they're at lower gravitational potential energy, right? And so essentially, that's like the jumping out of the airplane. I mean, that's pretty high up. But how was that energy released? Because they start off at high energy and end up at low energy, and we have conservation of energy. You know how that energy was released? Was due to friction on the slide, so their butt probably got quite warm from sliding down the slide, right? You'd get friction. If you put your hands there, you probably get burned, or your sleeves because you're going down. I think that slide's very fast. They're going quite fast down, so they might get what they call like a abrasion burn or something like that, going down like that because they're going so fast. And then that also reminded me, and this is because I like to go up in the snow. So I was at, unfortunately, I was up at Mammoth, and Mammoth is a big ski area. It's the biggest ski area, one of the bigger ones in California. I think it is maybe the biggest. Tahoe has some big ones too. But I was at Mammoth, and a 10-year-old slipped off the chair, and the chair is like 30 or 40 feet above the ground. And a person, I saw the person's friend was holding them by their shirt, just hanging there, and thinking, they should throw a rope or something, and lower them with a rope, because I like to do climbing and that kind of stuff also. So I know about rope handling and this kind of stuff. So I think, a safe thing would be to throw a rope or something. But instead, this was a snowboarder. So on one foot, they had a very long snowboard. And the person was hanging there, and maybe they didn't throw a rope because they were worried about how to get the rope around them and secure it and that kind of stuff. But I think if I was sitting next to that person, I would have asked them to throw a rope, shoot a rope, and then I would have tied it around them so that they could have been lowered off. But instead, they got about 30 people with one of these things that the firemen use when people jump out of the building. It's one of these parachute type things where they land on it, and they had her jump. She didn't remove the snowboard because if you think the snowboard got caught on something, it could easily break their leg or hip or knee or whatever else. But what happened was, when she landed on the parachute type thing, it's much thicker than a parachute. It slipped out of people's hands, and it was as if she just hit the ground. And fortunately, she survived, but with a broken neck. And I thought, my God, if I'm in that same situation, I'm never going to jump. No matter if those people are there, it's like the leap of faith. I just wouldn't do it. I'd figure something else out, or try to. And so I thought, man, it's like this building. If the building catches on fire, I was thinking, what do you have? You know, but yeah, so it was a tragic, thing that happened when I was there. Unfortunately, and there's a bunch of videos of that accident. But now, you know, there's a new rule at Mammoth and all Altera resorts. Altera is the company that owns them, that you have to lower the bar. They have a bar, but and there's like a penalty now. But before you didn't have to. There wasn't a penalty. Now you have to. I think they're being sued. You would imagine they'd be being sued right now, probably. But still, it shouldn't happen. What's that?
At Baldy, you don't have to. They don't require you
Do they even have the chairs at Baldy are so old? No, I remember going to Baldy the first time. I fell off because the chair you're used to having a little bit of weight, and the chairs are super light. And so I went to sit down on it, and I accidentally knocked it out, and I landed on the ground. It was pretty embarrassing.
No, they're still old and they're still pretty suspicious looking.
Yeah, Baldy is pretty scary. The lifts there, but
It has gotten better though with their lifts.
I like Baldy a lot.
So is the energy in this model just heat?
So the energy for that person that was dissipated went into breaking their neck, basically, and we're breaking bones. You know, that's where the energy's got to go somewhere, right? It would be nice if it was dissipated in heat, and that's fine. So I was thinking about that. You know, how could you evacuate somebody off a chair safely? You know, so maybe you guys can invent something that they can use at ski resorts. But yeah. Well, I was thinking I'm going to start carrying a little rope, you know, so I could rappel off the thing, save myself.
Methane and oxygen energy release just heat.
Methane and oxygen is heat is one, sound is another. So do you hear the roar of that? Sound is creating or dissipating energy. But there are other ways. The CNG bus that I was following, you know how they dissipated the energy? What they use is they don't use the CNG for generating electricity. They inject it directly into gasoline. So rather than having gasoline go into the combustion engine, which creates mechanical energy, because in a gasoline engine you have a little explosion and it drives a piston, and that piston drives a crankshaft, and the crankshaft drives the wheels. But rather than using gasoline as a fuel, they inject the methane in there to do that. And so methane and propane are often used, but the problem with methane and propane is the tank doesn't last very long. So it's okay for like a forklift. A lot of forklifts run on propane. Propane burns pretty cleanly, not as cleanly as methane. And then there are people running methane. If you go to the board, I was looking at methane too, because I thought, wow, that's a pretty interesting. So I was looking at the boards. A lot of people who drive CNG vehicles carry an extra stash of methane illegally in their trunk. So they got a cylinder full of methane in case they run out, because the CNG stations to refill it are far apart. That's not NSTA approved. And so it's all like hush. But you think, you know, it's kind of dangerous because you got a lot of potential energy there. The other thing I was looking at is a hydrogen vehicle, like the Mirai. And so I was talking, Mercedes also offered one. So I was talking to this guy who got one of the Mercedes one, and I said, don't you worry. I mean, if there's some accident, you know, hydrogen is very explosive. It was just like 2 years ago, a chemist in the University of Hawaii was killed from a hydrogen explosion. And so I was thinking, why would you want to have a hydrogen, like a tank of, why would you want to be sitting on a tank of liquid hydrogen? And how could you feel safe? And so he told me that, you know, before he bought it, he watched this video, and the video convinced him because that was enough evidence to convince him. And what they did was they flew it, I don't know, 16,000 feet over the California desert, and they dropped a full tank of hydrogen from that, and it reached terminal velocity and then hit, and no leaks, no explosion, no nothing. And so after that, he thought, okay, I'm going to buy it. And so he couldn't buy it because at the time they only leased them. I think the Mirai is also lease only. You can't actually buy it. But apparently the tanks are these carbon fiber things that can withstand tremendous mechanical impact and still survive. But you got to worry about potential energy, because potential energy, if it dissipates as heat, you can get too much heat and burn yourself. You don't want to cook yourself. And so we worry about that. But anyway, so we represent these models with this is the composition of the formula. The formula is the atomic composition, like 2 atoms of hydrogen, 1 atom of oxygen. So this would be a molecule of water. This is different because there are different ways to represent the composition of water. Another way of representing the composition of water is this: H11O89. Have you ever heard of H11O89? H11O89 is another way of representing composition of water, but nobody ever represents it that way. Do you know what 11 and 89 represent? 11 represents 11 grams of hydrogen for every 89 grams of oxygen. Because oxygen and hydrogen weigh different amounts. And so the oxygen atoms are much heavier. And so in other words, we call it 11% hydrogen by mass and 89% oxygen by mass. And so that's percent by mass. Percent by atom, it would be 67% hydrogen, 33% oxygen, or H2O, 2/3 hydrogen, 1/3 oxygen. So there are different ways of representing the composition, but the easiest is using atoms, Dalton's atomic theory. All right, so we look at states of matter. Actually, did I already talk about this? Kinetic molecular theory, right? Or maybe I didn't talk about this slide because we're out of time. So I got these slides from the morning class. Kinetic is motion. Molecular is just molecules. And so this is molecular motion. And it says it's a theory, but really this is based on the theory of chemistry. And the theory of chemistry is what again? Quantum mechanics. Quantum mechanics is the theory that describes chemistry at a fundamental level. And theories should do more than one thing. Not only should it describe things, like, that's what science does, is it just describes nature. Describes nature, we don't want to extend it too far, because science doesn't really, this is what Lavoisier did. Lavoisier just describes nature, right? Whereas alchemists do a little bit more beyond because they're doing the magic stuff, which is that kind of stuff. But what is this? Is this another theory? No, this is actually just based on quantum mechanics. And so they call it kinetic molecular theory, but it's just part of quantum mechanics. With kinetic molecular theory, we can look at things like molecular dynamics. Did I show you melting ice at the molecular level? Did we look at that molecular dynamics simulation? Yeah, converting into liquid, converting into gas. So that's all based on the quantum mechanics calculation. And so this is just molecular motion. You don't really see the molecular motion in static drawings here, so we try to visualize it more. At higher temperatures, what's happening with the particle? So when we're looking at motion, at higher temperatures, they're moving faster. At lower temperatures, they're moving. But, we can move them slower and slower, and pretty soon they stop moving. When they stop moving, it's zero motion. At zero motion, we have zero temperature. Zero temperature, we have zero kinetic energy. Zero kinetic energy, well, that's called absolute zero. And absolute zero, we call 0 Kelvin, Kelvin, which is equivalent to minus 273 degrees Celsius, which is equivalent to minus 454 degrees Fahrenheit. So we can't go colder than that, because how can you go slower than zero? Is it possible to go slower than zero? No. And so zero is the slowest we're going to go in any direction.
It's actually 273 degrees.
Yeah, minus 273 degrees Celsius is zero. Minus 273.15, to be more precise, is it. But that's zero motion. So let's move on here. We have different states of matter. Solid. There's This is the structure. Like ice crystals, they have well-ordered patterns of water molecules. Ice crystals, I saw that in the simulation. We also have amorphous solids, which don't have such good order. We'll talk more about crystalline and amorphous solids. I don't really want to talk much about this now. So you can ignore this for right now. This one amorphous, because when we get back to solids, then we'll look at them in depth. But we have solids, liquids, and gases. If you take a solid and heat it up, eventually it will melt into a liquid. And if you take a liquid and heat it up, it eventually will vaporize into a gas. And if you take a gas and heat it up, do you know what it turns into? The fourth state of matter. Do you know what the fourth state of matter is? A plasma. A plasma is a high energy gas. And what happens in a plasma is there's such violent collisions. These things are moving so fast that it knocks electrons off the atoms and creates. Do you remember this triangle thing? We want to understand things based on the structure and the composition and properties. I think this is a little aside. We'll talk about something else. This is not directly related to solids, liquids, and gases, although it's all part of properties. You know, properties are going to depend on certain things. We expect gases to have slightly different properties than liquids, or maybe significantly different properties than liquids and solids. So here we have. So if we take a solid, heat it up. Now solids, there's going to be no translational motion. What other types of motion are there in addition to translational motion? And what was translational motion again? Translational motion is the ability to move from point A to point B. But in the solid, the water molecules are kind of stuck at point A. And it's actually quite crystalline. That is, these are well ordered. Whereas liquid water is more amorphous. You know, the more amorphous, the kind of disordered, like that well ordered pattern.
What's the difference between translational motion and rotational?
Translational motion is you follow this water molecule, and does this water molecule have the ability to move up?
No.
It actually does. It's just slow going because it's sticky. It gets stuck. So this is like a crowded. Actually, does it? No, it doesn't. You're right. This is stuck. It's stuck because it's in the solid state, and so translationally can't move. But it depends on how stuck it is, because you might be stuck and still able to rotate in place. Water molecules can't. They're really stuck. And so there's no translational in ice. There's no rotational in ice. The only type of motion in ice is vibrational. So the molecules can vibrate. Did I show you the vibrational modes? I think I showed you the vibrational modes of water. There are three ways that water molecules can vibrate. And so these water molecules just vibrate. Now, if I heat it up, then I can break them free, but not completely free. And so now, if there's enough energy, the water molecules can translate and rotate and vibrate, but they're still stuck together. If I continue heating it up, then they're completely broken apart. And that's the gas phase.
But how is like them moving from one point to another different than them just rotating? Is it just like they?
No, one point to another means any point in the volume. Whereas rotation, it could stay in place and rotate. And so there are solids that have enough breathing space so that the molecule can spin and rotate. And so what happens in the solid, let's say there's a gap, like you see the structure of ice, there's a gap there. And if there's something in that gap that can rotate, then it can stay in place and rotate. And so we can have rotation without translation. It doesn't require translation to rotate. It just requires enough room to do. But that's at the particulate level. So this is kind of our trying to understand. We're trying to understand things at the particulate structure level. And that's going to explain some of the properties. So for example, some of the properties, this is rigid. The volume is rigid, the shape is rigid. Whereas the volume is fixed here, but the shape is, it can change. And the shape conforms to the shape of the container. So we talk about compressibility. So liquids are not compressible. Solids are not compressible, but gases are compressible. And so this is why they try to squeeze more hydrogen in the tank or squeeze more methane into a tank to get it. And so to this trying to reduce the amount of space. And so this is why they were looking at liquid natural gas. Liquefied natural gas has a lot less empty space, and much more dense for energy. And so you can read about these, the particle movement, so volume, macroscopic. And we have three types of motion: the translational, vibrational, rotational. We don't really talk about it here, but this is part of kinetic molecular theory because they have different equations that describe this. So if we want to be quantitative, then the total kinetic energy, and you're asking about how we calculate it. How we calculate the total kinetic energy is we have an equation for translational energy. We do physics there. We have an equation for vibrational energy. We do physics there, and an equation, and then just add them up. And that gives you the total. Is there any other equations that we have to worry about? No, there are no other equations that we have to worry about because this is all kinetic energy depends on. And so we just have three equations that we add up to get the total kinetic energy. Now, the potential energy is much more of a pain because there's not just one type of potential energy. There's multiple types. If it were just the bonds, it would be easy. But there's more to it than just the bonds. In fact, it's so complicated that the calculations are going to be way off. And so I'll make a long story short. That's very difficult to calculate. Okay, we have physical properties, and let's see, we start at 1. Yeah, we have physical properties and physical changes and chemical properties and chemical changes. So we talked about the chemical change. Methane plus oxygen with CO2 and water. That was a chemical change. And whereas water going from steam, which is initially what we have in the flame, to liquid water is an example of a physical change or physical property. Physical property would be condensation, which is the reverse of vaporization or boiling. The chemical properties, there's lots of different ones. You know, these are all the chemical reactions that happen. When we think about the chemical reactions, you know, do you know all the chemical reactions that happen in your body? It's too many, right? I mean, there's a lot of different things that can happen. So what we try to do is we try to subclassify those. Otherwise, this is enormous. You know, what are all the reactions? So you test it. Does methane react with fluorine? And you know what the answer is? Yes. Does methane react with nitrogen? Does methane react with et cetera, et cetera? And so, you know, how do we deal with that? Well, there are a lot of potential chemical reactions that can happen. And so that's going to change its chemical potential energy. And so, yeah, that was at Mammoth, that I think it was like 35 or 40 feet up. That just happened 3 weeks ago, I think, 2 weeks ago. All right, so here's the structure of ice. This is very well ordered. So this would be crystalline, we call it. Well, I'll talk about crystalline amorphous. If we were to freeze it like this would be more amorphous. There's not really a good pattern there. But liquids are all kind of amorphous like this. Some liquids are better ordered than others. They have liquids that are pretty well ordered, called liquid crystals. Have you ever heard of liquid crystals? It used to be a lot more common because the computer screens used to be made of these liquid crystals, LCDs, they call liquid crystal display. But anyway, most liquids are amorphous like this. But here we have the ice. So we have our three states of matter: solid, liquid, gas, and this one contains a fourth state of matter. Do you see the fourth state of matter?
density.
Yeah, here it is. The fourth state of matter is the plasma. So if you take a gas and keep heating it up hotter and hotter, you'll generate plasma. And plasma are common like the sun. The sun is a giant plasma ball, a giant flame. But there are other plasmas that aren't so familiar. You know, the flames of fluorescent lamps. These are not fluorescent lamps. These are LED lamps with the old fluorescent lamps. Neon signs are plasmas, etc. So there are a number of plasmas out there. These are examples of physical change because water stays water, you know. And so these are water molecules just in a different degrees of freedom. Degrees of freedom meaning you can do different things, but they're still water molecules. And so they can behave, they can taste like water. They're going to behave like water. However, this would be an example of a chemical change. If we take table sugar is sucrose, and we heat it up. We heat it up. Essentially, what we can do is we can melt the sucrose. If we melt the sugar and then re-solidify it, that would be an example of physical change. But sugar is very tricky to melt. Have you ever tried to melt sugar? What happens though is it starts to burn. You can melt the sugar. Let's say if you get rid of the oxygen, it won't burn. But what happens is the sugar will start to burn, and then we get like this caramelization. Caramelization. This would be an example of a chemical change. It's no longer sugar. So when we solidify this, I think caramelized sugar tastes better. I like it, but I don't like charcoalized sugar. Do you like charcoalized sugar? Yeah. And stuff. I try to go for this, but oftentimes I get this. But this isn't even complete because what happens when we have incomplete combustion with a Bunsen burner? What color is the flame?
It's like two colors.
The flame is a yellow flame, and the yellow flame originates from what? When we have incomplete combustion, we don't want yellow flames because there are two products of the yellow flame that we don't want. One of them is what causes the yellow color. The yellow color is actually black particles that are being heated up so that they start to glow yellow. And what are those black particles? No, not carbon monoxide. Those black particles are soot. And do you know what soot is made out of? Soot is made out of carbon, charcoal. This is charcoal. Do you like the taste of charcoal? No. So you go buy some charcoal, like briquettes for the barbecue, the old charcoal barbecues. They don't taste very good. Some people like charcoalized like marshmallows. You know, they like the black marshmallows. I don't really like. I like the caramelized marshmallow. But you get these black carbon deposits like this. Sometimes this is easy to clean. Sometimes it's very difficult to clean. So if you have a baking sheet and it's coated with black carbon deposits like this, how do you clean it? Carbon's very difficult to clean because it doesn't really dissolve in anything. It's hard to wash it away with soap and water. Because carbon, you know, when we think of carbon, there are different forms of carbon. Do you know the different forms of carbon? The structures of carbon?
Yeah, diamond.
Diamond is one structure of carbon. It would be great if you burnt your cookies and it resulted in little diamonds forming. Then you'd want to burn the cookies all the time because you can get diamonds. But then maybe diamonds would be like sand. And nobody's really going to care about diamonds anymore. Yeah, it's so rare. But that's one form. What's another form of carbon?
Cool.
Coal, there's different, coal's a mixture. Coal's a mixture of like what we call graphitic carbon. So graphite's another form of carbon, and amorphous carbon. You have different types of coal. So this is coal or charcoal or something like that. You can burn it. It's hard to burn, but you can burn it. And so graphite's another form, and then there are other forms. And so those are different structures for the same thing. Those are called allotropes of carbon. So we have diamond and graphite are the two big ones. And are diamonds and graphite elementally and compositionally they're exactly the same. So diamonds are 100% carbon, and graphite's 100% carbon, but their properties are quite different. And their properties are quite different because of what? The structure. And so do you know what a lot of people do to clean this baked on carbon? Baked on carbon like this is a process of incomplete combustion. What do you do for complete combustion? You just burn it more, right? You add more oxygen, you burn it more. And so what a lot of people do to clean this is they don't clean it because that requires a lot of muscle. Instead, what they do is they just cook it longer. They keep cooking it until the carbon is converted into, hopefully not carbon monoxide, because carbon monoxide is also a product of incomplete combustion. What's the product of complete combustion? Yeah, when it's complete. We know complete combustion because complete combustion results in what? Carbon dioxide. Why? And so what we want to do is we want to look a little bit, let me go back over here. This is complete combustion. The methane gets converted into carbon dioxide, but what happens if I add a third oxygen or fourth oxygen? Can I get even more complete combustion than this? In other words, I don't want carbon monoxide to form because carbon monoxide is poisonous. Carbon dioxide is potentially poisonous, but not nearly as poisonous as carbon monoxide. But carbon dioxide can survive. People drink it all the time, carbonated water, or whatnot. We exhale it with every breath, and so it's not killing us. Yeah, but at high concentrations, it could actually change our blood pH. But anyway, going back to this, could we go to carbon trioxide? That is, combust this further. Why or why not? Yeah, carbon dioxide is already stable, but there's another limit to this, and that is this. We can use the periodic table to determine like common charges. Like, what's the common charge on oxygen? Do you know what the most common charge on oxygen is? 2 minus or -2. That's the most common charge on oxygen. So if oxygen has its most common charge, that's -2 and -2. So think about this. -2 plus a -2 gives us a -4, plus X gives us 0, because carbon dioxide is not charged. Carbon dioxide is neutral. So what is X? -4 plus X equals 0. X is equal to +4. Now, let's say we had 3 oxygens here. If we have 3 oxygens here, that would be -2 plus a -2 plus a -2. That gives us -6. -6 plus X is equal to 0. X is equal to +6. Is +6 a viable option for carbon? And so I want to ask you, what is the range of charges expected for carbon? Not its most common charge, but what is the range?
4 to 1.
Okay. Well, how do you figure out oxygen's -2?
It's 2 spots away from the normal gas.
Yeah, it's 2. Oxygen's 8 here, and we're 2. So if we gain 2 electrons, we'll be like neon. Each electron is -1. So if we gain 2, we're neon with 10. Or we could lose how many to be like helium? We could lose 6. So oxygen can lose 6 or gain 2, which is easier? Gain 2. So 2. What about carbon? Carbon's kind of in a weird spot because carbon can gain how many? If it gain 4, it can be like neon, so that's -4. Or it can lose 2. It could lose 4 and be like helium. So the range of charges, we call these charges oxidation states, for carbon is between +4 and -4. Is +6 within that range? No, that's outside the range. And so +4 is maxed out. We don't expect +5, we don't expect +6. Does that make sense? So it's got to stay within that range. And so this is why we call this complete combustion or complete oxidation, As far as oxygens go, we can put one oxygen there, that's incomplete, or we put two oxygens there. With one oxygen there, you know what if we put one oxygen on there and make carbon monoxide, and we say that oxygen is -2, what must carbon be? If, okay, so -2 plus x is equal to 0. X must be 2. Plus 2 is not complete because a carbon can go all the way to +4. So this is why we call this incomplete oxidation, complete oxidation. Oxidation is what we call removing electrons. An oxidizer takes electrons away. Oxygen wants to take electrons away from carbon. And so that's what we end up with. So going back to this, here, this is not complete. Carbon in this state is 0. And so carbon's right in the middle. So carbon can either gain 4 or lose 4. And so in this case, you can just burn it further until it goes to. So the carbon will be, eventually it'll be converted into CO2. So what a lot of restaurants do is they got heavy carbon deposits on a lot of stuff, and they just cook it. They cook it on the flame to drive off, or cook it in the oven to drive off the carbon deposits, rather than try to clean them, which is tough. This stuff is tough to clean. It's like trying to dissolve pencil lead. Have you ever tried to dissolve or clean pencil lead? And wash it away? Does it wash away easily? No. So, all right, let's take a break now, since I've been talking too long. And then let's take a 15-minute break and we'll start up again after. All right, so we're going to talk about pure substances and mixtures. When we look at matter, we can subdivide it into substances and mixtures. Substances are pure, and so a lot of people just say substance. But sometimes people think of substance as a mixture, like sugar water. And technically, you might think, okay, sugar water is a substance, but it doesn't quite hit the definition, because the definition of a substance is it has to be pure. And so is there such thing as pure sugar water? And you would think, yeah, there is, because it could just be sugar and water. But what makes it not pure is that a pure substance has to have fixed composition. And so this one is going to have fixed composition. That is, it's only going to have one kind of matter, and therefore it's all like water. And based on having a fixed composition, it's going to have a fixed set of properties based on that composition. Okay, whereas mixtures will have variable composition. If they have variable composition, they're going to have variable properties. And so it could be sweeter or less sweet. Not only that, but the physical properties will differ as well. So, for example, if we have sugar water, you know, sugar water doesn't boil at 100 degrees C. Sugar water boils at slightly higher than 100. Whereas water, this is called a heating curve. And what's happening here is you're adding energy to water, or time. This is actually energy here. I don't know why I put time, because you can sit and wait for water. Maybe this is at 100, but anyway, we're adding energy to water. So water might start off at 25 degrees C. And with time, does water warm up automatically at 100 degrees C? Now you have to add heat, and heat is energy. So as we add energy, the water warms up. That is, water is absorbing energy to increase its kinetic energy, which means its temperature increases. But eventually we hit 100 degrees C. Do you know what happens at 100 degrees C? Its kinetic energy doesn't change, but do you know what changes? It's potential energy, because it goes from liquid to a gas. And so there is a difference in potential energy between liquid and gas. However, between liquid and liquid, let's say water 25 degrees C versus water 50 degrees C, it's just higher kinetic energy. Its potential energy doesn't change. What changes in terms of the potential energy, and this is why I say it's a little bit more tricky to calculate, is because we're breaking the water molecules completely free from each other. Okay, anyway, with a solution like this, the temperature, the boiling point actually increases.
So does liquid water have more potential in it, or is it gas?
Gas. Gas, gaseous water, steam, has more potential energy. And so what would you rather be, you'd probably rather not be burnt by either of these, but what would you rather be burnt by? Would you rather be burnt by a pot of water at 100 degrees C? Or would you rather be burnt by a cloud of steam gushing out of a pipe at 100 degrees C? You need to go, both of them are at the same temperature, so won't both of them lead to the same severity of burn? No, do you know which one's going to give you a much worse burn? Steam burns are going to be much worse than water burns, even though they're both at the same temperature. And how could that be? Well, it's because steam has higher potential energy. And so what happens is, when you try to boil water, you have to add energy to boil. And so when we boil water, we have to add energy to boil the water. Temperature doesn't change. And therefore, when we condense water, we have to remove energy. And so all this energy has to be removed. Well, that's not kinetic energy you're removing, it's going to be potential energy as it condenses back to liquid at 100 degrees C. We'll talk more about this later when we talk more in depth about energy.
It feels like both of them are connected. Wouldn't gas have more kinetic energy than liquid water?
Yes, they're connected in that sense. That's true. The gas, but it's tricky because in general, gases do have more kinetic energy. That's how you break them apart, right? However, in this case, they're both at the same kinetic energy because something happens, and it's weird at the boiling point. At the boiling point, you're dumping in a whole bunch more energy, but the temperature's not changing. And so the temperature's not changing, where's all that energy going into? That energy is going into breaking apart the potential energy. And so at this temperature, the kinetic energies are the same. They're no different, but the total energy is different. And so the gaseous has much higher total energy than the liquid water. Does that add up? And then once we convert all this to steam, do you know what happens if we add more energy to steam? The temperature of the steam increases, and so we can get hotter steam. So if you're at 120 degrees Celsius, then you have superheated steam, basically.
So at the boiling point, kinetic energy is the same as it was before it was at the boiling point.
Right.
But the potential energy has not increased.
Yeah, that only happens at the boiling point. The same thing at the melting point and the freezing point. At the freezing point of water or the melting point of water, you're adding energy to melt. So if you add energy to melt the ice, is the temperature of the ice increasing? So ice melts at 0 degrees C, and you continue adding heat. Does it get hotter, or does it stay at 0 degrees C? Do you know what the answer is? It stays at 0 degrees C. Have you ever seen this? This is later on in this chapter. Let me go back. I guess I closed it, but let me go back to it. I closed it, but have you ever seen
Listen, there's a good chance somebody's trying to hack your website right now. You gotta make sure you're covered.
If we take an ordinary paper cup and
Normally
heat
we
the
heat
paper cup,
water and boil it in a
it
glass
very
beaker.
quickly bursts into
Like this. This
flames.
is a Pyrex beaker. This is a paper cup.
If we take
We
a
wouldn't
paper
want to
cup
heat the paper
and
cup over
put water in
flame,
the
would
paper
we?
cup,
But
it doesn't burst into flames.
What's happening here
You can
is
actually
the
boil
cup there
water
is filled
in
with
the paper
water.
cup.
So what's
The water
happening to
has a
all that
very
kinetic
high
energy?
specific heat
All the
due to its
energy of the
hydrogen
flame is not
bonding.
going into
It also has
increasing
a
the
high lower
temperature
heat of
of the paper
vaporization,
cup.
also
Because
due to
when
the
the
hydrogen
paper cup
bonding.
hits a certain temperature, like
The water
marshmallow,
absorbs heat
it'll catch on
rapidly,
fire. You know
and
the
so
paper cup
rapidly
doesn't go above
that the
100
paper
degrees
never
C
gets up to its
as long as
kindling
there's
temperature.
water in there.
We've added a little
So you
food
put the
coloring
paper
to the
cup in
water so it
flame,
makes
you
it
can boil
easier
water
for
in
you
a
to see the
paper
water
cup.
boil.
And what's causing the paper cup not to burn is it's not getting hot enough to burn. That's why. And so all that, where's all that energy going into? All that energy is going into potential. It's not going into kinetic energy. It's weird, isn't it? But you can boil water in a paper cup, no problem, over a flame. This is another form of carbon here. It's called C60. But anyway, so people take advantage of these properties. So one of the properties is the more concentrated. That is, the more concentrated the sugar is, the higher the boiling point. The less concentrated, the lower the boiling point. And at zero concentration, it's just at 100 degrees C. And this not only works with sugar, but it also works with salt. So salt water has a higher boiling point. That's one of the properties of that particular mixture. But the boiling point is variable depending on how much salt you put in there. So, like some people boil pasta, when they boil pasta, they put a pinch of salt in the water. Okay, when they put the pinch of salt in the water, is that to increase the boiling point? Because for cooks, have you ever heard this rule for cooks? For every 10 degrees C temperature increase, you cook things twice as fast. So let's say I'm cooking food at 100 degrees C. If I can increase the temperature to 110 degrees C, it should cook twice as fast. So let's say it takes 14 minutes to boil pasta at 100 degrees C. If you boiled it at 110 degrees C, how long would it take? It should take half as long, 7 minutes, because it's going to cook twice as fast, right? And so this is the whole concept behind a pressure cooker. A pressure cooker is you want to increase the pressure so that water boils at a higher temperature. But this could also happen with salt. But the situation is, so there was some debate, and there's still some debate. Is the salt added to increase the boiling point, or is the salt added for taste? And it turns out that a pinch of salt barely increases, and so it's almost close to pure water. And therefore, the salt is just for taste. In order to really increase the boiling point, you'd have to put like a fistful of salt. If you put a fistful of salt in the water, then you'll see a noticeable increase, not by 10 degrees C, but maybe by 3 degrees C or 2 degrees C or something like that. If you have a small increase, then that's still going to result in faster cooking times. On the other hand, water boils at a lower temperature at high elevations. The air is thinner at higher elevations, so there's lower pressure. And so at high altitude, we need longer cooking time. So have you seen high altitude cooking directions? Like, for example, if you're making a cake in Denver versus making a cake at sea level, then you're going to need extra time. You need extra time, you might need extra water or other things to cook it. It depends on the pressure, the air pressure. And so the higher the air pressure, the more energy you need to boil the water. The lower the air pressure, the thinner the air, the less energy you need.
Is it harder to make a fire like in a very high mountain?
It's more difficult. You probably because the air is thinner. If you have more oxygen, it's easier. So, but I don't know if it's harder. People can make fires at higher elevations. They can fan the flames. Have you heard fanning the flames? They're just trying to get more oxygen, get more complete combustion. But I would imagine at much higher elevations, it gets harder and harder because you get less and less oxygen. And so pretty soon, rather than getting a blue flame on the stove, you get a yellow flame, or worse off. Lots of soot. All right, so we're looking at pure substances versus mixtures. So here we have bromine, a pure substance. Bromine is an element, but if you look at this element, it consists of two atoms in a molecule. And this is called a diatomic molecule. Bromine likes to pair up, likes to bond with another bromine to form these two atom molecules. There are other elements that like to bond together. Do you know which ones? Like to pair up to form diatomic molecules. Iodine. Iodine likes to pair up like this. So when we look at the element iodine, we call I2 rather than just I, because I likes to pair up. There's 7 of them that you need to memorize. So bromine's one, iodine's another, I2. What's another one? Oxygen. When we breathe oxygen, it's O2 we're breathing because oxygen likes to pair up. And that's the most stable form of oxygen. But what's the blue color in the flame from? Do you know what the blue color in the flame is from? It's from oxygen atoms. So in the plasma, the oxygen molecules get broken apart to make atoms of oxygen. The atoms of oxygen collide and get excited. And they don't stay excited forever. Eventually, they're going to drop down in energy. And when they drop down in energy, there's conservation of energy, and they spit out blue light. Blue light's energy in the form of light. And so the blue color is from atomic oxygen. Atomic oxygen is not as stable as diatomic oxygen or molecular oxygen. So when we're breathing, we don't want to breathe atomic oxygen. You might have breathed in or inhaled atomic oxygen in the form of like ozone. Ozone decomposes into diatomic oxygen and oxygen. Have you ever breathed in or inhaled, like if you have an electric spark or lightning bolt, you might smell the ozone in the air. It's somewhat corrosive. Yeah? No? Okay. Well, anyway, so that's oxygen. That's what we have: iodine, bromine, oxygen. It's 3. What else?
Chlorine.
Chlorine, 4, Cl2. Chlorine's a green gas. What else? Nitrogen, this is N2, that's 5. Fluorine, yeah, fluorine is F2, that's 6. One more. Hydrogen, that's 7. And so off the periodic table, it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are the diatomic elements. And those in pure form are going to form diatomic molecules. Now, what state are they? Most of those are gases. Hydrogen, nitrogen, oxygen, those are all gases. There's one liquid. Do you know what that one liquid is? Bromine is the one liquid. And so pure bromine is a liquid like this. And there's one solid. Do you know what the solid is? Iodine. Iodine's a solid. Purple crystals of iodine. Most of the elements on the periodic table are solids. The next most common state are gases: hydrogen, oxygen, nitrogen. And the least common state are liquids. There are only 2 liquids on the periodic table. Do you know what the liquids are on the periodic table? Bromine's one of them. What's the other liquid on the periodic table? Mercury. So those are the 2 liquids. So we can take pure bromine, which is liquid, and we can take pure water, which is also liquid, and then we can make a mixture. And it depends. The mixture's composition is variable, so we can add different amounts of bromine. So this is a small amount of bromine, which we call a more dilute solution. And here's a greater amount of bromine, which we call a more concentrated solution. So we can make a dilute solution of bromine or a more concentrated solution, and the color will be different, as well as some of the properties will be different. The boiling points will be different, and other things, density will be different, etc. And so those are mixtures there. Now, when we look at it at a macroscopic level, homogeneous and heterogeneous refer to what the mixture looks like or what the substance looks like. And so if it's homogeneous, it has a uniform appearance. And so when we go back to these all look homogeneous to the visible eye and to the naked eye. And so this is homogeneous, 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 homogeneous. So just because it's homogeneous, you can't tell if it's pure or mixture. So this mixture at the macroscopic level looks homogeneous. At the particular level, you can see it's heterogeneous. There are two different types of particles here. And at the macroscopic and homogeneous, at the particulate heterogeneous. Well, all these will look homogeneous, and these will be homogeneous at both the particulate level and the macroscopic level. Now, if a mixture is homogeneous, then we call it a solution. So solutions is a little bit out of order for me. Homogeneous mixtures are solutions. And then we could have homogeneous substances or pure substances, which would just be elements or compounds. Elements like bromine or compounds like water. Compounds are two or more different elements that are bonded together. Phase just refers to solid, liquid, gas. And if we have multiple phases, then that's what we call heterogeneous. So sand and water would be heterogeneous, and that would be a mixture of sand and water. Heterogeneous usually indicates a mixture, but sometimes heterogeneous can be pure. Can you name something that's heterogeneous and a pure substance? Hmm? Yes. So I'm just being redundant, emphasizing the pure. Can you think of something that's heterogeneous but a substance, a single substance? Ice water. Ice is pure water. Liquid water is pure water. So ice water is the. So ice water would have uniform composition because it just is made up of water molecules, but with different phases. So there's one exception here that we can think of ice water. But most everything else that's heterogeneous is going to be a mixture. Like oil and water. Oil and water don't mix, so you can see that there would be two different liquid phases for that, and that would be a heterogeneous mixture.
So is phase like a phase part of homogeneous?
Phase, homogeneous has a single phase. Heterogeneous has multiple phases. A phase is like solid, liquid, gas. And so, let's take a look at an example. Okay. There's a single phase here, and it looks uniform. Therefore, this is what we call homogeneous. All these are homogeneous. But can you tell which ones are pure and which ones are mixtures? By looking at it. No, you can't tell. This is a homogeneous pure, or just a homogeneous substance, which is just water, pure water. Do you know what this one is? This is also pure, but it consists of these molecules. These are bigger molecules. These are molecules of ethanol. So this is pure ethanol, which is liquid. Now, pure ethanol and pure water share similar properties. They're both colorless liquids. However, other properties are different. So ethanol is going to have a different boiling point. Do you know the boiling point of ethanol is lower than that of water? And in other words, ethanol evaporates and boils easier. And therefore, we call ethanol more volatile than water. So water will evaporate just slowly. Ethanol evaporates quite a bit faster. We can mix these together. So ethanol and water can mix in all proportions. So this is a mixture of ethanol and water. And we can have different concentrations. It can be highly concentrated or dilute. This is an example of a heterogeneous mixture. Even though it's the same phase, the phase is solid, but it's heterogeneous because you can see these are crystals of iron here attached to the magnet. You can see them pulling out crystals of iron. And then we have sulfur here, powdered sulfur. These are actually sulfur crystals here. And so this is a mixture, heterogeneous mixture of iron and sulfur. We can separate out the components of the mixture. The components would be what the mixture is made up of, and in this case it's iron and sulfur using a magnet. And so we can pick out the iron and leave behind the sulfur. This is an example of what we call physical separation. The physical separation is separating we can use physical separations to separate the components of a mixture by using their physical properties. And in this case, we're using the physical property of magnetic. So once these iron filings attach to the magnet, they're still iron, so you can remove them. Nothing's changed with this identity. Yes?
So referring back to the moment, that's how you separate salt from ball bearings as well?
You can separate salt from ball bearings if the ball bearings are magnetic. A lot of ball bearings are magnetic. It depends on what metals they're made out of, but some ball bearings are not. Like if you get to like 304 stainless steel series, those are non-magnetic. So you wouldn't be able to separate it that way. There are other separation techniques. We use a magnet. There's something called distillation. Distillation takes advantage of different boiling points. So we can easily make a mixture, but how do we separate it? Separating out mixtures is a lot more difficult. So for example, here, this is so easy to make. Just pour the ethanol in water, and we get a mixture of ethanol and water. But now we want to reverse this. I want to go back to pure water and pure ethanol. How would I do that? I can try filtering it out, but is there a filter that's small enough to capture the ethanol, but big enough, to let the water molecules pass through? Is there such a filter? And actually the answer is yes. People have developed filters that are so small we call them molecular sieves. And with these molecular sieves, they try to capture the big molecules and let the small molecules pass through. So that's one way you can try to do it. You can try to separate it via filtration. That would be an example of a chemical or physical. That would be an example of a physical separation techniques trying to take advantage of the size.
I thought ethanol was bigger.
Ethanol is bigger than water. So what I mean by capture is the ethanol can't pass through. And so the ethanol is captured, but the water can pass through. The holes are small enough to pass through water, but too small to pass through ethanol. Does that make sense? And so people have tried to separate, this room is filled with nitrogen and oxygen. And this happened when I was at UCSB. I was working on the floor, and one of the labs there, they were working on molecular sieves. These filters that were so small they can pass through some molecules, but leave other molecules behind. So nitrogen and oxygen are two different sizes. So they're trying to find a molecular sieve that could pass through. What's bigger? Do you know which one's bigger? Nitrogen or oxygen? You would think oxygen's bigger, but it turns out it's not. Nitrogen's bigger, oddly enough. We'll talk about why later. That has to do with the theory, but for right now, nitrogen's bigger. So they're looking for a molecular sieve that passes the oxygen but leaves the nitrogen behind. Why? Why? Because do you know how people get oxygen right now? How people get oxygen right now is they liquefy the air. Have you heard of liquid air? Liquid air is a gas company, and what they do is they liquefy the air, and they take advantage of the difference in boiling points. And so what happens is they'll boil off one and leave the other. That's called distillation. And so when we were talking about this, one way of separating ethanol from water is by taking advantage of the difference in boiling points. Ethanol boils at a lower temperature. And so what we can do is we can start heating this up. When we heat up this mixture, the ethanol boils off first, leaving behind the water. And that way we can separate the ethanol from the water. All right. And so traditionally, if you want pure oxygen and pure nitrogen, one way to separate the mixture here is to liquefy it and then boil off the more volatile one. But the problem is it's very expensive because in order to liquefy it, you have to cool it down. In order to cool it down, it costs a lot of energy because This is what we call cryogenics. I mean, the temperature is very cold. You aren't going to be able to do it with a freezer, a traditional freezer. You need to get it extremely cold. And getting it extremely cold costs a lot of money. So one of the reasons they want to use the molecular sieve is to hopefully reduce the cost, because they can do this at room temperature. Well, the molecular sieve isn't so functional because nitrogen and oxygen are very similar in terms of size. So what they did was they put an electric field on the molecular sieve. And it turns out that they take advantage of another property of nitrogen and oxygen. Oxygen turns out to be a little bit magnetic. It's what we call paramagnetic. And so it's attracted to magnets, whereas nitrogen is not. And so in addition to the molecular sieve, they put an electric field there. And then it still goes very slowly because you got to push things through the filter. Normally we use gravity to push things through filter, but we can't use gravity for gases. And so they use a pump. And so there's a company that got started. This is from research at UCSB. And the company that got started is they have these molecular sieves with a little pump and a fan. And so rather than carrying around a big oxygen tank, they carry around a little battery and a fan pack and the molecular sieve, and then they can have the oxygen come here. So some people, 21% oxygen is not enough. Some people need enriched oxygen, but they don't need 100% oxygen. They just need enriched oxygen. And so they don't have to carry around these big tanks. So people with reduced lung capacity used to walk around with these big heavy metal cylinders of pure oxygen on a tank, but now they carry a small pack like this. And this is a company that was started in Santa Barbara and Goleta. And it was quite an idea. It was a great idea because now you can get rid of the tank. You don't need a tank. You just generate the oxygen as needed. And so you pass it through the filter, the molecular sieve. And that's how it works. And now it's a huge company. And you think, wow, why didn't I think of that? Because, you know, a lot of people were talking about molecular sieves at the time. And then it turned out to be quite successful. But separating out mixtures is always a challenge. You know, sometimes it's easier, sometimes it's more difficult. It's one of the big challenges in chemistry, because in chemistry we're often dealing with mixtures. And so separation techniques are quite important in analyzing, because many times we're dealing with mixtures. So here we might have a mixture. This could be like salt water. And we want to separate out pure water from this. And it turns out the boiling points of salt is very high. And so what we can do here is we can heat this up and boil the water. When the water boils, it gets converted into steam. And the steam goes through this. This is a tube. This is a double-walled tube. And so this is a tube with a hollow center. And the steam goes in the hollow center here. On the outside of this tube is a jacket. And this jacket, what they do is they put cold water in here. And when the steam hits the cold water, it condenses back into liquid water. And we get pure water. So this is distilled water. Distilled water is expensive because we have to boil the water. Boiling water costs a lot of energy. So we have a much cheaper alternative here. The much cheaper alternative is DI water. DI water goes through essentially like a molecular sieve. So what the molecular sieve does is it removes all the impurities out of there. Although it doesn't act, its action is kind of like a filter, but it's not like a filter like the sieve I was talking about. It's a little bit different. And so our DI water is we take our tap water and put it through deionization tanks, which extracts the impurities out of there. But our DI water is still expensive. Do you know how much our DI water costs us? Our DI water costs us 60 cents a gallon. And so in the past, we've run out of money. This is actually more common than you might think. We run out of money. We don't have the budget to have more DI water. And so that means we can't use any DI water. So what we do is we have a bunch of jugs of DI water in the stockroom in case we run out. When we run out, that is when eventually those things get, they don't get clogged, but they get saturated with impurities and they have to be replaced. And we don't have the money to replace them. So we switch from the tap to the jug, we can tell when our DI water's gone bad because a lot of the experiments will get some weird results. And then we can test when our DI water's gone bad because DI water doesn't conduct electricity. It should be an insulator, whereas tap water conducts electricity. So we just measure the electrical conductivity of the water, and we can easily see how good our DI water is. And so this is why we ask everybody to conserve our DI water so we don't run out until we get the next budget. And we don't have enough money for the amount of DI water we want to use. So just do that. UCLA doesn't have this problem. In UCLA, I got to use distilled water for a lot of my experiments, and distilled water is a lot more expensive. Not only did I use distilled water, I used something called DDW. DW is distilled water. DDW is called doubly distilled water. And doubly distilled water is extremely expensive because what they do with doubly distilled water is first they deionize the water, and they distill it once, and then they distill it twice. And then after the second distillation, then they hit it with UV to kill any organisms that might be growing. And so it's extremely pure. And so some of my experiments, the deionized water wasn't pure enough. I had to use something even purer than deionized water, closer to. And the purity depends on how much you want to, this says pure, but it depends on how much you want to spend. When I used to purchase helium, some of the highest grade helium had 6 nines, 99.9999% pure. That means there are some impurities here, but this was extremely expensive. This is ultra high purity helium. Do you think I'm going to fill balloons with this? No, it's so expensive. You don't fill balloons. If you want 100%, you're going to be paying a lot of money because it's hard to purify. It's hard to separate some of these mixtures and get all the impurities out. And so for things like silicon chips, that's probably close to 100% because each impurity there means they have to throw away the chip, and that could be a lot of money. And so, when we say pure, yeah, it's fairly pure. Okay, this is a regular filter. This is just gravity filtration. So we just use gravity to go through filter paper here. Filter paper comes in these circles like this, and you just fold it in half, again, you get a quarter. I was always taught this: rip off one corner, and then open it up. When you open it up, you get 3 layers on one side, 1 layer on the other, and you put it in. And they said turning off a corner helps. But I never asked why. What evidence do they have to support this? I've always been taught tear off the corner, so I always tear off the corner until I got lazy. And I thought, why do I tear off the corner? I don't even want to tear off the corner. So I stopped tearing off the corner. So I don't even bother tearing off the corner anymore. Because you know what? I noticed zero difference. So if I noticed zero difference, then based on my observations, I didn't see it was worth it. So I don't bother tearing off the corner, but every manual you read, they say tear off the corner. And then I'll just filter it. So this would be heterogeneous. This would be like sand water. And so we can separate out the sand from this is not water, the color's wrong, from the liquid, whatever that liquid is. And so we can use filtration. This is another example of physical. There's nothing's changed chemically. Okay, when we think about pure substances, we have 2 types of pure substances. The pure substance could be an element like diamonds, graphite, silver, or it could be a compound like water. Pure water, not tap water. Tap water is a mixture. All right, so when we're typically dealing with matter, we divide it. Is the matter a mixture or is it pure? Sometimes we can tell by its look. If it's homogeneous, can you tell if it's a mixture or pure? If it looks homogeneous. If it looks homogeneous, then we don't know if it's pure or compound. And so typically what we do is we try to separate it or look at its properties. So if it's homogeneous, we might take it and then try to separate it using like distillation or filtration or whatever. Filtration doesn't work so well because it's homogeneous. However, if it's heterogeneous, then chances are it's a mixture. And so if something's heterogeneous, most likely it's a mixture. If it's homogeneous, it could either be pure. If it's pure, what is it? If it's pure, it's either a element or a compound. And so if we have something that's homogeneous, it could be a mixture, it could be a compound, or it could be an element. If it's a mixture, we try separating it into its components. When we separate it, like salt water, we can separate out the salt, which would be a compound, from the water, which would also be a compound. Or it could be bromine water. If it's bromine water, we could separate out the bromine, which is an element, from the water, which is a compound. So for mixtures, we try to separate the mixture into pure substances. Now the elements, we stop there. But for compounds, we can try to separate that. So if I have water is H2O, and I can try to separate the hydrogen from the oxygen. But I can't use filtration for that. I can't use distillation. In order to separate the hydrogen from the oxygen, I have to use chemical means. And the chemical means would be like a chemical reaction. Do you know how to separate hydrogen from oxygen in water? You can do this at home if you wanted to. Let's see. This isn't the greatest video here. Let me find one more. This is only 33 seconds. Let's use this one. If you keep it in the water, one of these, what we call electrodes here.
How to get the most of Grammarly Free. It's Kayla on behalf of Grammarly to tell you all about the free version of the best communication.
So this is called chemical separation or electrode separation. Electrode because it's electricity. It's hard to see, but there are bubbles being produced here and there are bubbles being produced here, but there are twice as many bubbles being produced here. Do you know what elements being produced here? It's hydrogen, which is going to produce twice as much gas as oxygen because we have twice as much hydrogen than oxygen. And both of those are diatomic. So this would be H2, this would be O2 over here. Now, do you know what is this the positive or the negative? And so when we look at the battery, this is the big one, and this is the small one. The big one, is that negative or positive? You know? It turns out it's negative. This is the negative, this is the positive. So at the positive, we produce oxygen gas. At the negative, we're producing hydrogen gas. So this is one way we can do chemical separation. And the properties are going to be quite a bit different in the chemical separation.
The charges have to be like hydrogen being like a +1 charge?
Exactly. The charges have to do. Hydrogen's +1, oxygen is -2. So what's happening here is this is positive, means the battery is trying to suck electrons into it. This is negative, which means the battery is pushing electrons out. And so what's happening here is the oxygen is losing. Oxygen normally has 2 extra electrons, -2. And so oxygen is losing those electrons, and then the neutral oxygen atoms are coming together to form O2. O2 has no charge on it. And the hydrogens are usually +1, and then now they're going to 0 in order to go from +1 to 0.
Will it become an acid since it's coming to 0?
It's not. It is an acid already. Water is an acid. Did you know that? Water is an acid. But the weird thing about water is it's also what we call a base. and it's equal in terms of strength. So water is equally strong as an acid and as strong as a base. So what we say is water has a pH of 7, you know, and we'll talk more about it later, but. And so we normally think of as water as being neutral, but water can act as an acid, no problem. And water can act as a base, no problem. All right. So eventually, what happens here is we take a compound like water and we separate it by chemical means into the elements of hydrogen and oxygen. But sometimes we can take a compound, separate it by chemical means, and get another compound, a different compound. So let's say we're trying to separate carbon dioxide. It might involve multiple steps. We might go from carbon dioxide to carbon monoxide, and then from carbon monoxide, the elements carbon and oxygen. So it could be multiple steps here. But ultimately, what we want is we can break all matter into elements. And so all matter, whether it's a mixture or pure, this would be pure down here, this would be a mixture up here. We can break these all down into elements here. And so matter is made up of the elements. Let's look at some elements. Over here we have gold. But is that, you know, for example, if it's 18 karat gold, is that pure gold? 18 karat? What is pure gold? What carat is pure gold? Is it 25? It's 24 karat, right? 24 karat gold. Everybody wants 24 karat gold because 24 karat gold is pure gold. And so we know that this could be 24 karat gold, then it's pure gold. But if it's 18 karat gold, then do you know what 18 karat gold is? 18 karat gold is 80% gold. Is it 80% gold? Is it 80% gold? Or is it 80% gold? Or is it 80.0% gold? Are they all the same? No. And so I don't know how precise the definition is. If the definition is, it's 80% gold, then 80% gold, somebody might think, oh, okay, 80% plus or minus half the smallest digit, which would be 10, let's say. It could be anywhere from 84 to 75%. You know, 75% gold is close enough to 80%. Is that precise enough? Well, it depends. Maybe if you buy 18 karat gold, you're only getting 75% gold, depending on what the definition of that is, right? Or maybe the definition is a little bit more precise. So 80 versus 80 dot. 80 with the decimal point here means a little bit different. This means it's more precise. That means that this is significant. So this is just certain to the tens, so 80, 90, 100. This is more certain to the ones. So it's not 79, it's not 81. This one, if it's 81, it just rounds to 80. You know? If it's 85, it'll round to 90. So this one is a little more precise. So this is 80 plus or minus half the smallest unit. Half the smallest unit would be 1, so it'd be 0.5. So this one ranges from 80.4 to 79.5. So do you see this is a much more precise definition of 18 karat gold? And so if you buy 18 karat gold, you might have just bought 79.5% gold. Or you might have gotten lucky and gotten 80.4, you know, a little bit more gold. But it's a mixture because mixtures composition varies. Or maybe it's 80.0. 80.0% is a lot more precise. And so the range is a lot smaller. This would be 80.0 plus half of 0.1. Half of 0.1 is 0.05. So it'd be anywhere from 79.95 to 80.04. And so if the definition of 18 karat gold were 80.0%, then the lowest amount of gold you're going to get is 79.95. Otherwise, it doesn't meet the definition. And so how precise is that definition of 18 karat gold? Is it this precise? Or maybe it's more precise than this. Could it be infinitely precise? Do you think that would be easy? to get the, no. It would be very difficult to get it with no uncertainty. So, I don't know the answer. Does somebody know the answer? I would think it's like this. So there's a chance you might get 75%. And that's close enough. Or maybe this. Anyway, going to this is silicon. This silicon has to be extremely pure. And so they have all kinds of techniques. They have a technique called recrystallization to get extremely pure, like just about 100% silicon. Very few impurities in there. I think this is like gold plate here. This is copper. This is lead, but this looks heterogeneous because there's some kind of brass in the lead. And I'm not sure how pure that lead is. I don't think that's so pure because high purity means expensive because it means they have to separate out the impurities. This is probably like 98%, so it's a mixture. This graphite is easy to get pure though. And so graphite is usually very high purity. These bolts look homogeneous, but they're really heterogeneous because underneath this, you know what this coating is on the bolt? This coating is zinc, and the bolt is made out of steel, which is also a mixture, or iron. And this coating is to sort of act as an antioxidant. They don't want the bolt to oxidize because it'll rust. And so the zinc is an antioxidant. But sometimes the zinc gets corroded away and then the bolt will start to rust. This is called galvanization. Pure copper is expensive, so pennies are no longer pure copper. Do you know what's in the center of pennies? Zinc. So pennies are copper-coated zinc. The zinc is easily corroded, so is serving as an antioxidant for the bolt here. And so to prevent the zinc from being oxidized, the zinc in the penny is completely encased in copper. Copper is very resistant to corrosion. But sometimes there's a chip in the penny, so you can end up with hollow pennies. The chip gets in there and the zinc corrodes out of there. Or sometimes kids eat the pennies. And the pennies have a chip in there, and then their stomach acid will dissolve the zinc and cause zinc poisoning. So we're worried about that. Here's some compounds. Drain cleaner, sodium hydroxide. I doubt this is pure. This probably has some impurities, or it's probably 98%, close enough to be pure. This is probably pretty pure here, chalk. Baking soda. Although it says pure here, I don't know how pure it is. It's hard to get 100% purity because of small impurities getting introduced in there. And so we represent these substances with formulas. So we have elemental formulas. So for example, hydrogen, we don't usually write H. Do you know what we write for H, for hydrogen? If somebody says, I have a tank of hydrogen gas, what are they referring to, H or H2? They're referring to H2. Hydrogen likes to pair up. Or if somebody says they have a tank of oxygen for diving, it's not O. It's O is going to kill you because it's going to be very corrosive. It's O2. O doesn't last very long because it will pair up with other oxygen. Whereas helium likes to be alone. There's no problem with helium. And then we have substances here. Like HCl, H2O, BaCl2. We call H2O water, but there's another name for water, which was what? What is that again? Dihydrogen monoxide. That's fine, 2 hydrogen, 1 oxygen. How should we name this? Should we name this barium dichloride? And the name is not barium dichloride. Why don't they call that dichloride? They don't call it dichloride because barium is what we call fixed charge ion. What's the charge on barium? So take a look on the periodic table and find barium. Do you see what group it's in? It's in group number 2, near the bottom. Do you see it? Can you tell me what the charge is? It's not negative. It's plus. it has a much easier time losing than gaining. So barium is +2. And then take a look at what chlorine's position on the chart is. What's the common charge on chlorine? -1. And so we don't have to call this barium dichloride because we know we have to have 2 chlorides for every barium. And the reason we have to have that is because the compounds have to be electrically neutral. So if we have a 2+, then we need 2 of these negatives to balance out the charge. And so this is never called barium dichloride. It's just called barium chloride, and then you use the charges to figure out how many of each you have. Whereas for water, we could have different ones. We could have dihydrogen monoxide, or we could have the other one. We could have H2O, or we could have what was the other one? H2O2. H2O2 is called hydrogen peroxide or dihydrogen dioxide. And so they're different ones, and it's hard to figure out because oxygen has, well, -2 is the most common charge on oxygen, and therefore we need 2 hydrogens, but oxygen can also have a -1 charge. It's not very stable, but it can. So that's what could lead to potential confusion there. Atoms are the smallest part of an element. Molecules are the smallest particle of molecular compounds, but there should be one more here. Not everything forms molecules. Not all compounds form molecules. Can you name a compound that doesn't form a molecule? Salt. Does salt form molecules and these molecules packed together? No, salt forms what we call formula units. Formula units is the smallest unit of anything. Smallest unit of anything. And so we could use this. A formula unit of gold would be a gold atom. A formula unit of helium would be a helium atom. A formula unit of water would be an H2O molecule. A formula unit of salt would be 1 sodium and 1 chlorine, or 1 sodium chloride unit. It doesn't form molecules because it doesn't form discrete units. We'll talk more about that later, but we should just add formula unit to this. There. Then pure substances obey the law of definite composition. The law of definite composition, law of constant composition, means pure water anywhere has the composition H2O. It doesn't matter. That's the law of definite composition, the constant composition. Dalton used this as evidence in support of observations in support of atomic theory. And how did he use this? How he used this is water always forms 2 hydrogens and 1 oxygen. And it makes sense if the smallest unit were atoms. We could have 2 atoms of hydrogen, 1 atom of oxygen. But what if there was no such thing as the smallest unit? If there was no such thing as the smallest unit, then it wouldn't be unreasonable to have different ratios. Just say water with a little bit more hydrogen or water with a little bit more oxygen, because you can just have a little bit more because you can divide this into smaller and smaller quantities. And so it's like well, anyway, what it is if you believe in infinitely divisible matter, that is, if you didn't believe in atoms, then it would be hard to argue about the law of constant, harder to argue about the law of constant composition, because if you're trying to mix, let's say you're trying to mix flour and sugar. Each time you mix it, do you always get the same ratio? Let's say you need 3 cups of flour, 1 cup of sugar. Are you mixing those to exactly the same ratio each time? Or sometimes you get a little bit more flour, sometimes you get a little bit more sugar in the cup, measuring cup. And so this is the argument against, because if matter were infinitely divisible, then it would be like mixing flour and sugar. You can accidentally put a little bit more sugar or accidentally put a little bit more flour and change the ratio just a little bit, right? Because it's continuous. However, if you're looking at sugar cubes, then as being the smallest unit of sugar, then you're limited. You can have like one sugar cube is the smallest or two sugar cubes. So you're going to be fixed. And then the flour, if you're looking at bags of flour, then those are going to be fixed. And so when we have discrete units, then we're going to get discrete ratios of constant composition. So this is one of the arguments in favor of Dalton's atomic theory, law of constant composition. What were some of the other arguments in favor, or the other argument in favor? The other argument in favor was the conservation of mass, the conservation of matter. So atoms are important. We also need to learn how these atoms interact with one another. And so in order to do that, we need, actually, maybe before I do that, let's talk about this, since I talked about this in the morning class. Mixtures are very difficult to analyze, and sometimes mixtures are like almost impossible to separate. So let's say you're looking at a petri dish of tumor cells. Can you separate that petri dish of tumor cells into a whole bunch of pure substances? Wouldn't that be really hard? In fact, do you know in the cell, let's say in the human cell, do they know everything that's inside a human cell? Have they identified everything inside a human cell? Yes or no? Are there still stuff that they don't quite know? They know it's there because of the mass, and they know it's there because of the function, but they don't know what its identity is, what its formula is. And so there's a little bit, even in the human cell, you think, well, they have it mapped out. Well, they don't have it completely mapped out because there's still some stuff that's not quite figured out, right? Well, this brings up a study. Well, you can still do science and still not know all that, but one of the things they did was at the University of Michigan, they were looking at a petri dish of cancer cells, and they were trying to figure out if electric fields, that is, if I put a positive and a negative piece of metal in there and turn up the voltage, like 9 volts, 10 volts, 20 volts, 100 volts, will that inhibit the growth of the cancerous cells? And so what they did was they put it, but they didn't put any metal in there because metals are susceptible to oxidation, except certain metals. Some metals are very resistant to oxidation, like copper. Copper is pretty resistant to oxidation, whereas zinc isn't. Zinc is easily oxidized. But copper isn't as good as what? Because eventually copper corrodes. It isn't as good as silver, and silver isn't as good as gold. Gold is excellent, because gold is very resistant to oxidation. So we don't have to protect gold from oxidation using some antioxidant like zinc. Gold is used in electronics. Things get hot. But you know what else is good? Platinum. Platinum is really good at resisting oxidation. So what they did was they hooked up the battery. Actually, they have a power supply, but essentially it's like a battery. They hooked up the battery to 2 pieces of platinum, and then they stuck the platinum in the petri dish. Now, platinum is very resistant to chemical reaction. Platinum, gold, silver, and copper are called the Nobel metals. The Nobel metals are chemically very unreactive, and so they put the platinum electrodes in the petri dish and then cranked up the voltage. And then what they wanted to see is having a positive on one side and a negative on the other side, does that screw up the growth of the cancer cells? And do you know what they saw? They saw the platinum started to react with the culture medium. So the platinum started to react. It was very unusual because platinum is so unreactive, like gold. It's really hard to get it to react. But anyway, it reacted. Whatever the product of the reaction was, killed all the cancer cells. And so they thought, wow, it was very effective at killing the cancer cells. And so they wanted to figure out what it was. And so what that meant was they had to separate that complex mixture, cancer cells plus the product of this platinum, into the components. The components would be pure substances, but that was impossible. And so do you know what they did? What they did was they opened up a catalog, a chemical catalog from manufacturers, and they went and they bought every single platinum compound that they could find in the chemical catalog. And then they went through and they tested all of them. So for example, they bought this is called transplatin. They bought transplatin and tested it. It didn't kill the cancer cells. And then they bought cisplatin and they tested it. And you know what happened with cisplatin? It killed all the cancer cells. And so they found it. And it turns out it was cisplatin that they generated at what we call the electrodes, at the platinum wires. And this turned out to be extremely effective. And it's extremely effective. Look at the composition. Do you see something interesting about the composition of transplatin versus cisplatin? Yeah, the composition is the same. So the composition is the same, but the structure is different. And so structurally, cisplatin works, transplatin doesn't work. And they didn't know why it works, but it worked very well. And they went on to market it as a chemotherapy agent. Chemotherapy is a chemical therapy agent for cancer treatment. I think it's breast cancer they use it for. And it turned out to be very effective. Later on, somebody figured out how it works. You know how it works? It's pretty interesting. How it works is, what happens is cisplatin gets lodged into the grooves of DNA. And when cisplatin gets lodged in the grooves of DNA, it prevents replication. And so the cancer cells stop growing. Whereas transplatin doesn't. And why that is it's because of the interactions between the molecules, the DNA molecule and the platinum molecule. What types of interactions are these? The types of interactions these are electrical interactions. And so when we think of quantum mechanics is looking at the electric interactions between atoms and molecules. And so essentially this is quantum mechanics. At a very simple level, we can simplify quantum mechanics into electrostatic forces. Electrostatic forces are attractions and repulsions between charged species. And the attractions and repulsions go like this. Like charges repel. So two positives repel, two negatives repel. Unlike charges attract. And then based on this, we can generate a law. And this is an empirical law. And the law is Coulomb's law. And so we take some measurements and we come up with Coulomb's law. Coulomb's law is that the force is, actually we'll just do, force is proportional to the charge, which we call Z, on A and the charge on B, divided by the distance between the centers of charge squared. And so if we double the charge, we double the force. So if we double A and double B, we quadruple the force. And so it depends on the magnitude of the charge and the distance. We call this charge density. So this is what the force is proportional to. Here we can see electrostatic interactions. If you take the glass rod and rub silk on that, then the glass rod acquires a positive charge. That is, some of the electrons off the glass rod rubbed on the silk. And then you can transfer that charge over to these pith balls, and you can charge the pith balls. If you charge both pith balls positively, they repel each other. So this is a positive being spread apart. If you rub fur on this is just Coulomb's law in action. And so this is what happens. When the water molecules stick to one another, they're sticky because of electrostatic attractions. When this platinum gets caught in the groove of DNA, there's electrostatic attractions there that are causing it to stick in the groove of DNA. All right, we talked about chemical equations already, so we did this. This is burning off. So we have baked on carbon deposits. We can burn it off with oxygen and convert it to CO2. So this is clean, let's say you're baking pans by further heating it in oxygen. Here, this is the battery. So here what we did was we took water, threw a 9-volt battery in there, added some salt to speed things up, and that resulted in the chemical separation of hydrogen from oxygen. We form twice as much hydrogen as we do oxygen, so we'll get twice as many bubbles of hydrogen from oxygen. These are all balanced. These are balanced by matter and mass, but these are not balanced by energy. Over here, we have to add energy. And so energy plus this will give us this and that. Oddly enough, this one releases energy, but we have to heat it up, otherwise it happens too slow. So we have to add energy to get it hot enough to start to react. Once it starts to react, this should release energy. It should be exothermic. When we have to add energy, like the 9-volt battery, that's called endothermic. We're adding it here. Oftentimes we don't balance the energy, even qualitatively, but sometimes we do balance out the energy. So here, this is butane. Butane's a liquid. And so we take butane, which is C4H10, and burn it. And so we take 2 molecules of butane, 13 molecules of O2. We're going to make 8 molecules of CO2, 10 molecules of water, liquid, and energy. This is the exothermic. This is going to result in a butane flame. And so there are butane stoves, butane lighters, butane heaters. Now, the energy, what we'd like to do is there's 2 types of energy. What are the 2 types of energy? Potential and kinetic. This has higher potential energy. This has lower potential energy. Butane is very flammable, so this is an unstable mixture here. What we want to do is we want to keep the kinetic energy the same. So we start off at 25 and we end at 25, even though this is going to get very hot because this is going to be a flame. So the initial kinetic energy and the final kinetic energy are the same, but in between the kinetic energy increased. The temperature got hot. And eventually, as that cools down, it dumps off that excess energy. So we get hot CO2 and hot water. But we want the hot CO2 and hot water to cool down so we get the maximum amount of energy released into what we call the surroundings. This is exothermic. We can also have endothermic reactions like this. This is photosynthesis, where we take CO2 and water. CO2 and water make wood or cellulose and oxygen. And so trees do this. This would be endothermic. The reverse process of this would be exothermic. And this is at a lower potential energy. This is at a higher potential energy. So this would be a plant at room temperature. Does the plant get hot or cold? No, the plant just stays. The plant doesn't have any way of regulating its temperature, so the plant just stays at the same temperature. And so here, the kinetic energy didn't change. It changes the potential energy here. And so we have to add energy for this to happen. It's the endothermic reaction there. It was noticed, we have conservation of energy and we have conservation of mass, but it was noticed for nuclear reactions that some of the mass disappeared. So let's say there was a nuclear explosion. What happens is it doesn't weigh the same amount. That is, you might have 10 grams at the start, but you're going to have less than 10 grams at the end. And so for nuclear reactions, we see that some of the mass is converted into energy. So we don't have conservation of mass, nor do we have conservation of energy. And so when we're dealing with nuclear reactions, we have to do conservation of mass and energy combined. And so therefore, if we lose a little bit of mass, we must have gained energy. Or if we lose energy, we must have gained some mass. This also turns out to be true for chemicals. The changes are so small that the conservation of mass and conservation of energy for chemists stays the same. If you're a nuclear chemist, then we would worry about mass not being conserved and energy not being conserved and the relationship between mass and energy. And so you'd have to be aware of that. And so that ends chapter 2 there with the law of conservation of mass and energy here. But for us, we can treat these separately. For us, it doesn't really change chemical changes. In nuclear changes, though, we would use the first one there. So this is why, if you notice here in the definition, they say chemical change. And up here, it's for anything, nuclear and chemical. So here's conservation of energy, but we have different kinds of energy. And so energy is neither created nor destroyed, so energy can be converted in different forms. The energy is still all there. So, when we burn the methane, where did the energy ultimately end up? Well, we heat a pot of water, but where did that energy end up? And eventually all that energy, where it ends up as? All the energy, let's say you generate electricity, eventually all that energy ends up as heat. Heat is what we call the least useful form of energy. But, all the energy is still there. Okay, I'm going to stop here. How much time do we have? We have 5 minutes? 4 minutes? Let's see how fast you are at your memorization. How well did you memorize this stuff? And so, can you do this in 4 minutes? This is Claire's here. So you have the long weekend. You might have started the memorization. You might not have started the memorization, but don't wait till the night before the test to memorize these. You try to memorize these sooner than later. All right, well, officially time's up. Therefore, if you have to go, you can turn this in on Monday, or you could stay later if you want and finish it. But how many did you get out of the 10? Two? So that's one for every 2 minutes. Should anybody get more than 2? 0? Any zeros out there? 1, 2, 3, 4. You got 4.
I'm gonna upload this one.
Yeah, I'll upload this one. You can. It'll be on week 2 module.